Researchers at the Florida Institute for Human and Machine Cognition have created a test bed for development and evaluation of improved telerobotic surgeon interfaces called the Anthrocentric Multisensory Interface for Sensory Augmentation of Telesurgery, or AcmiSats. It uses a full-body wireless motion capture system to control the robotic surgical system components while relaying sensory feedback information to the surgeon using visual, auditory, and tactile displays. The AcmiSats testbed consists of a modified computer motion Zeus surgical robot and Mimic Technologies DaVinci S HD trainer, and the process could be extended to other systems. The system can be controlled using natural motion gestures and allows the surgeon to perceive the elements of the procedure using the brain's natural ability to integrate information arriving from multiple sensory channels. These elements reduce the workload and improve learning when operating complex surgical robots. Rather than using a foot pedal to clutch and unclutch the robot end effectors and endoscope, AcmiSats allows the surgeon to use a natural clenched fist gesture to engage the clutch. While clutched, the robot becomes locked into its current position until it's unclutched. Clenching the right fist clutches the robotic arms, and clenching the left hand clutches the camera. By tracking the surgeon's head in 3 dimensions, we can automatically change the orientation of the view camera based on the surgeon's head movements to create a dynamic viewpoint that provides perception of depth through motion parallax. Unlike 3D movies or stereoscopic endoscopes, AcmiSats provides a dynamic, 3-dimensional viewing experience without special spectacles that naturally changes with the movement of the head. A surgeon can return the robotic arms to a favorable working position at any time by engaging the clutch and then extending only the thumb, index, and middle fingers on the right hand while leaving the left hand clutched. Energy dissection and cauterization can also be applied by using hand gestures during a surgical procedure, removing the need for the use of foot pedals. To activate energy dissection or cauterization, one can simply change the configuration of the hand. After grasping the tissue, extending the small finger and the ring finger simultaneously will engage the dissection function. For cauterization, the surgeon touches the same fingers to the thumb while clutching a blood vessel. Repetitive tasks can become more burdensome in robotic surgery in comparison to open procedures. AcmiSats incorporates a follow-me function that allows the surgeon to define a number of actions, then instruct the robot to execute a series of these actions. Demonstrated by using a pick-and-place practice drill, the surgeon records complex, repetitive tasks and can instruct the robot to execute these tasks. An additional gesture allows the surgeon to create what is called a no-fly zone. To create a no-fly zone, the surgeon touches the right thumb with the right little finger. A no-fly zone is a spherical volume of space that the surgeon identifies as an area to avoid. If the actuators encroach on this area, the surgeon will receive an auditory or tactile spatially relevant warning that indicates the approach or violation of the no-fly zone. In addition to the normal endoscopic video imagery provided in surgical robot systems, AcmiSats employs spatial audio and tactile displays to create a coherent multisensory perceptual experience. For example, it currently provides information about the force and position of the graspers using a WeCob incorporated BrainPort electrotactile display. This non-visual interface transmits information via a high-resolution electrotactile stimulator that is placed on the surface of the tongue. To provide improved perception of the locations and forces on the shafts of the robotic arms beyond the field of view presented on the video monitor, AcmiSats presents the position of the robotic arms intuitively as tactile vectors on a forethought development videotact electrotactile array worn on the abdomen. Both displays can provide position data spatially and forces as intensity, but without interfering with the fine motor control of the hands and fingers. Manipulations of our software can transform any of the tactile cues into spatial auditory cues. Grasper closure angle can be represented in surround sound using fore and aft sound position, while grasper closure force can be represented with modulation of tone frequency. The dimensional audio also proved effective for use as a spatial warning system to identify potential collisions between robotic arms and no-fly zones. The reduction in workload associated with more intuitive, multisensory interfacing should allow a single surgeon to manage 2 simultaneous cases. AcmiSats utilizes gesture-based switching between simultaneous procedures, or between members of a surgical team. To initiate a change, the surgeon makes a clutch gesture to lock the current procedure robot. He or she then turns to face the video monitor for the other case, unclutches to release its robot, and proceed with the case. Alternatively, multiple surgeons can operate the same robot on the same patient at the same time. One surgeon can trade control of the robot by clutching his or her controls as the other surgeon unclutches and takes over control. The AcmiSats approach should allow better utilization of surgical robotic technologies by decreasing surgeon workload and improving safety. It could also improve or enable routine remote telesurgery and telementoring and improve the quality of care available to a patient in a rural hospital or distant battlefield by allowing a team of surgeons to safely and efficiently operate as a team, even if they are located in separate facilities from each other and the patient.